Okay, so you'll have to bear with me a little bit today. We have a green background, or we have a purple background. I forget what. And green writing again. Hopefully they get this fixed. However, my 10 o'clock class, I didn't get to record the lecture, and so therefore I need to record this one so I can post it for them. For half of them didn't make it. So we have some questions on Wiley. 2.5, what questions?
Like is on the written assignment.
On the written assignment? Okay, which one's on the written assignment?
Actually, the same on the
2.5, number 15?
15.
13, sorry. Okay, 2.5. See if I can zoom in a little bit here. Okay, so 13. So that's your question, 13? Do you know the product or the quotient rule?
Yeah.
Do you know the derivative of a cotangent? You know the derivative of cosecant. So
I tried, but the answer there was like different. So.
was your the same answer, just not simplified? So let's go through and do this one, I guess. So this is 2.5, number 13. So 2.5, number 13. What do we have? The function f of x equals cotangent of x divided by 1 plus cosecant of x. So this is our problem. Is it somewhat better if I zoom in and you can't see much of the paper? Or if I keep it zoomed out? This is good? Okay. All right, so let's look at the derivative of this function. F prime of x. What's the derivative of the top?
Minus cosecant squared.
Yeah, negative cosecant squared.
Hold the bottom, right? Minus the derivative of the bottom. What's the derivative of 1 plus cosecant squared?
Cosecant x, cotangent x.
So cosecant x, cotangent x. Hold the top over the bottom squared. So now we might need to get into simplifying some trig stuff, which shouldn't be that difficult. So I have minus cosecant squared x minus cosecant cubed x minus cosecant x cotangent squared x on top. This one, I distributed this term. So 1 plus cosecant x quantity squared. Is everyone?
Wait, so cosecant times cotangent.
Here?
Yeah.
Cosecant times cotangent is cosecant times cotangent squared.
Oh, you just did that. Okay.
So now, it turns out I can pull out a.
Excuse me.
Go ahead.
So, the derivative of cosecant, isn't it minus negative cosecant cotangent? So we have plus on the top.
So this is negative, so cosecant cotangent. So yes, this negative here becomes this positive here.
And you don't, what he asked for the cosecant, you just multiply, when you multiply these two?
Here,
Uh-huh.
this is like x times y times x, which would be written as y times x squared.
Okay.
You wouldn't multiply the x times each term. Here you distribute it because you have 1 plus something. Okay, so now I need to simplify some things. So this doesn't look like the answer that's in the back of the book, but we can simplify it. So it turns out, if you recall, possibility, so we have this sine squared x plus cosine squared x equals 1. If I divide through by, what do I want to divide through by?
Would this answer be okay for a test?
Sine? Yeah, this answer would be okay for a test unless it says fully simplified. So if I divide this through by sine, I have 1 plus cotangent squared x equals cosecant squared x. Various ways to simplify trig functions. If I get a 1 plus cotangent squared x, I can write that as cosecant, sorry, not secant, cosecant. Cosecant squared x. Right? So that might possibly give me something to simplify what I want to pull out. I can pull out a cosecant in everything. So if I do that, see, if I pull out a negative cosecant, what's that going to give me? I'll just pull out a cosecant. I might need to pull out a negative. We'll see. So this gives me minus cosecant x minus cosecant squared x plus cotangent squared x. So cotangent squared, or cosecant squared, I need to pull out a negative, right? Because 1 equals cosecant squared x minus cotangent squared x. So you see, if I pull out a negative, I get that, and I can replace that with 1. So if I pull out a negative here, this becomes positive, and this becomes negative. This whole thing here is 1, right? Anyone have any questions on that? So then I have a 1 plus cosecant of x, right? That cancels with the 1 plus cosecant of x and one of the 1 plus cosecant of x in the denominator. So I end up with minus cosecant, I'll go ahead and write this out, cosecant of x plus 1 Is that what the back of the book gets?
I think they're like equal tangent.
Do they convert it? So 2.5, number 13. 2.5, number 13. That's exactly what the back of the book does. So you can see on 2.5, number 13, minus cosecant of x over 1 plus cosecant of x. So this is our derivative. With trigonometric functions, there are a million identities out there. And if you get to Calc 2, you'll do trigonometric substitution for integration, and you can get 5 different students can do it, and they can get 5 different answers that are all correct, that they all equal the same thing. So trig's fun, right?
Does that make grading it difficult?
It makes grading it, yeah, relatively difficult. Except in Calc 2, there's one easy way to do it, and there's multiple really hard ways to do it. So I kind of motivate the students to do it the easy way, and they'll get the same answer. But okay, any other questions? 2.5? 2.5 on Wiley. Did you guys have plenty of time to get your Wiley assignments done? I pushed back 2.6 until the 1st, which is tomorrow at 11 p.m. So I don't know if you guys saw that, but we have a quiz on the books for today, or on our schedule, but I'm going to push it back, and it's to be announced. I'll figure it out. So today, when I get back to my office, I'm going to post this lecture, post the notes, and then also I'm going to send out an email with when the written homework's due, when our next exam's due, what's going to be covered, and just kind of get you guys back on track on the plan. I'll probably also update the schedule. If you notice in the schedule, we have, I think, an extra day that we were only going to take a quiz. We might have to do some lecture and a quiz that day, but I think we'll be okay on getting back on track.
Will it be like online, please?
I haven't decided yet, so as soon as I know, I'll let you know. Okay, so today we're going to cover 3.2. 3.2 is very useful in upper level calculus, also in upper level physics and engineering. It gives you a new technique to find derivatives. So 3.2 is the derivatives.
I thought you said last time we were going to do another example of 3.1.
Did I give you guys?
I just
Yeah, I'll do some more examples from 3.1 after 3.2. I'll kind of then pull up Wiley and go some examples. Let's see if I can zoom out just a little bit. You guys still see that okay? Okay. So derivatives of logarithmic functions. So our goal today is to obtain a formula formulas for logarithmic functions, well, they're derivatives. So I'm going to go through the proof, and then we're going to also talk about why the natural log is favored over log of any other base, right? Because I can take log of base 2, or base 10, or base 8. You guys did probably a lot of that manipulation of log of different bases, change a base formula, things like that. The reason why change a base formula is so nice is because you can put everything in base E. And when it's in base E, the derivative is a lot easier to do than the derivative of any other base. So let's just get started. So recall, we talked about the limit as x goes to infinity of 1 plus 1 over x to the x power. Do you guys remember what this is? Might give you a hint. We're talking about ln, natural log base E. So this was E. And another way I'm going to write this is I'm going to substitute, I'm going to make the substitution v equals 1 over x. So if you notice, v goes to 0 from the right as x goes to infinity. V also goes to 0 from the left as x goes to minus infinity. Can you guys see that? 1 over something. So this is getting closer and closer to 0 on the right. This is getting closer and closer to 0 on the left. So if I make this substitution v equals 1 over x, I'm going to replace the limit. Instead of x going to infinity, I'm going to have v. V is going to go to 0. So then I have 1 plus v, 1 over v power. And this still goes to z. We're going to use this in our proof. Of what is the derivative with respect to x of ln of x. So I'm not expecting you to pull this out of thin air. I will expect you to use it once you find out what the derivative of ln of x is. But we like to show things. Why is the derivative of ln of x what it is? So let's start with what is the derivative of ln of x? The only way we know how to show something is by the definition, right? So we would take the limit as h goes to 0 of ln of x plus h minus ln of x over h. That's the definition of the derivative. Now I want to clean it up. So recall if I have ln of a minus ln of b, I can write that as ln of a divided by b, right? So on the numerator, I can write this as the limit as h goes to 0 of ln of x plus h over x, all divided by h.
Is that an equal sign between those?
Yeah, that is, sorry. Right, everyone follow that step? So now here's kind of the trick. See where I want to go to. Well, I'll go ahead and say, okay, let v equal h over x. So as h goes to 0, v is also going to 0, right? Because x is just a variable. So as v goes to 0, as h goes to 0. So now I can rewrite this as the limit as v goes to 0 as the ln of x plus v over v times x. You guys see h is v times x? I just rewrote h is v times x. If you would have never thought of it, it's perfectly fine. I'm not expecting you to prove this on any exam or on the final. But this is just kind of the derivation of the derivative. So now I'm going to be a little tricky. I'm going to go ahead and write this like this. 1 over x times v times, right? I really want to get it in this form, 1 plus v to the 1 over v, because I know I can replace that with e as v goes to 0. So this 1 over v is a constant out front, right? And I can move that to a power, right? If you recall, r ln of a can be written as ln of a to the rth power. So I get the limit as v goes to 0 of 1 over x times ln of x plus v to the 1 over v power, right? Which is great because this is exactly what I wanted. So I get 1 over x times ln of e. What is ln of e? No. ln of e, 1. ln of e is 1. So I get 1 over x times 1. As v goes to 0, I get 1 over x. So that tells us that the derivative with respect to x of ln of x is 1 over x. Just kind of a side note here, I can never take natural log of a negative number. So x always has to be positive. So sometimes your book will use absolute value to always make that true. So this only makes sense when x is a positive number. When ln of something, but that something has to be positive. Right? So sometimes your book will say the derivative with respect to x of ln of the absolute value of x is 1 over x. So you're not going to just have ln of x to deal with. You might have ln of a function to deal with. So the chain rule would state that the derivative with respect to x of a function that's ln of u would be 1 over u times du dx, where u is a function of x. Question?
Like the whole v thing,
Mm-hmm.
can the limit exist if they're not going to the same thing?
They are going to the same thing. Here, you mean? Like this v substitution?
Well, because like as v goes to 0 from the right and v goes to 0
Mhm.
from the left, those two limits don't equal each other.
Well, here I'm saying, how is the relationship between v and x? If x goes to infinity, v goes to 0, right? If x goes to minus infinity, v goes to 0, but always negative. And negative 0 on the left and 0 on the right is still going to 0. So if I make this substitution in this limit, which we know from college algebra, then I have to change x is not going to infinity. X is going to infinity when v goes to 0. Does that make sense? So here I made the jump x and v. And then nicely here, h was going to 0, v was also going to 0. I just put in an x there. X is any variable. So it gave me the ability to simplify this into e and then take ln of e to be 1, so I get 1 over x. The nice thing about ln of x is the derivative is 1 over x, but natural log is the inverse of e to the x, right? But the inverse of 2 to the x is log base 2, right? You might have dealt with logs in college algebra, change of base, various different types of manipulation of logs. But really in calculus, e to the x and ln of x are the key bases to use. We really never use base 2. We can, it just doesn't come up. So let's look at, okay, if I have log base 2 of x, what would be the derivative of log base 2 of x? Well, that's going to be 1 over ln of 2 times x. I can show this by change of base. So let's look at change of base. If I have log base b of x, and I want to do change of base to ln of x over
You're running out of space.
ln of b. Oh, thank you. So pull this up. So if I take the derivative of log base b of x, I can take the derivative of ln of x over ln of b. And the derivative of ln of x is 1 over x. ln of b is just a number. It's a constant. ln of 2 is ln of 2. You guys remember change of base formula? Maybe not off the top of your head, but have at least seen it before. So in this case, if I differentiate this relationship with respect to x, I get 1 over ln of b times 1 over x. So I have this constant to deal with. So maybe not. We'll just put, this is just a number to deal with. So when I'm taking log base 2, I have 1 over ln of 2, which is just a number, times 1 over x. So that's why we like to use ln of x before any other bases, because ln of x, if I do the derivative with respect to x of log base e of x, that's 1 over ln of e times x, which is simply 1 over x, because ln of e is 1. So let's look at applying this to some examples. So let's look at number 6. What is going to be the derivative with respect to x of ln of the absolute value of x cubed minus 7x squared minus 3?
This is 3.2 in both numbers?
Yes. So the derivative of the outside, which is 1 over the inside, times the derivative of the inside. So the chain rule is in effect here. So I have 1 over x cubed minus 7x squared minus 3 times the derivative of the inside, which would be 3x squared minus 14x. Right? So I could write that as all one expression. Derivative of the outside, the formula is 1 over, right? This is really ln of u. And the derivative of ln of u is 1 over u times the derivative of u. U is just a function of x. Do you guys see that?
So that one is just like a constant.
What is?
Like the derivative of the outside function, the ln, is like a constant, like 1 over x. Like the 1 over ln, anytime we say like ln, it's like 1 over x.
Yes. The formula or the form for ln of something, the derivative of ln of something is 1 over that something times the derivative of that something. Question?
Will we be taking the second derivative ever?
Possibly, yeah. Definitely, second derivative has notations in physics. The second derivative is acceleration. So you might want to know something about the acceleration.
So we Just use the quotient.
then you would end up using the quotient rule. Okay, so let's look at some problems on Wiley. Oh, sorry, we're not quite done with. Okay, so now that we know how to find the derivative of ln, there's a technique called logarithmic differentiation that becomes useful for complicated functions. So let's look at logarithmic differentiation. The technique of logarithmic differentiation is when you have a complicated function, you can take natural log of both sides, simplify it, then differentiate it and solve for dy dx. So let's look at a messy function. So granted, this is not a horrible function. That's a 4, by the way, sorry. We could differentiate this. It would take some time. The derivative of the top by itself is messy. Hold the bottom, pretty messy. Take the derivative of the bottom, not too bad, but hold the top, it's ugly. So it's hard to see what's going on here. So logarithmic differentiation is when you take ln of both sides, then differentiate, and then solve for dy dx. So let's do that. So we have ln of y equals ln of x squared, the cube root of 7x minus 14 over 1 plus x squared to the 4th power. So I don't want to differentiate until I simplify. So I can simplify this, right? If I have ln of a times b divided by c, that's ln of a plus ln of b minus ln of c, right? And that's basically what I have here. So I have ln of y equals 2 ln of x plus 1/3 ln of 7x minus 14 minus 4 ln of 1 plus x squared. I also pulled the powers down as coefficients, right? This. I went the other way, though. If I have a to the rth power, I can write it as r ln of a. Does anyone have any questions with that? Simplifying logs?
That's just what you did with the first one, the ln of the x squared. Right? That's the only
Yeah.
time you did that.
And I also, this is a 3rd power, so I brought that down here. And this is the 4th power, I brought that here.
Okay.
So I did it on all 3 of them.
So when you take a log and you have and you're subtracting them, then you can write it as dividing. And if you have dividing, you can do this.
If you take ln, so if I have something like ln of a times b over c, I can write that as ln of a plus ln of b minus ln of c. And then I also have powers to deal with that I can pull down front. So now that we get to this part, I want to take the derivative of both sides. So I take the derivative with respect to x. What is the derivative of ln of y with respect to x? Huh? What's the derivative of the outside? 1 over y times dy dx, right? Dy dx is important. We need that because that's what we're solving for. But then we also need this 1 over y. Derivative of the outside evaluated at the inside times the derivative of the inside. In logarithmic differentiation, a common mistake is not taking 1 over y times dy dx. So that's the derivative of the left-hand side. What's the derivative of 2 ln of x? 2 over x. What's the derivative of a 3rd ln of 7x minus 14? Right, we can write it, you guys see each part of that. So I could throw the 3 in there. I could also pull out a 7 and cancel the 7 on top, but I'm just going to leave it like this until I simplify it. Minus 4, 1 over 1 plus x squared times 2x. How many people think this is a lot easier differentiating term by term than differentiating this mess? Yeah.
So how do you get this second one?
Here? Because it's the derivative of the inside. What's the derivative of 7x minus 14? 7. What's the derivative of 1 plus x squared? 2x.
So you're like using the chain rule there.
What?
You're using the chain rule.
It is the chain rule. Yeah, the derivative of the outside would be 1 over the inside times the derivative of the inside.
So are you multiplying by that 7?
Yes. Question.
So the natural log of any number is 1 over, or the derivative of it is 1 over that number?
The natural log of a function. The derivative of the natural log of a function is 1 over that function times the derivative. The natural log of 5, the derivative of natural log of 5 is 0, because that's just a number.
That's why you used u earlier, right?
Yes, because I want to say it's a function of x. So yeah, I think you're along the right track. Just throwing in a number doesn't make sense, because natural log of a number is a number, and the derivative of a number is 0. But natural log of a function is 1 over that function times the derivative of that function. That's the form, right? So now I'm not done because I want to solve for dy dx. So to get rid of this y, I need to multiply this side by y. So if I multiply the left-hand side by y, I multiply the right-hand side by y. Do you guys see that? So now I have dy dx by itself. I have 2 over x plus 7 over 3 times 7x minus 14 minus 8x over 1 plus x squared, all multiplied by y. But what is y in terms of x? This super ugly thing, right? But it's super ugly. We can copy it, and it's not too bad, right? So that is our derivative, right? And that's called logarithmic differentiation. Logarithmic differentiation is a technique you will use in Chapter 3 later on. 3.6, we're going to learn L'Hopital's rule, which has to do with evaluating limits. And one technique, when it's undetermined, like 1 to the infinity power or 0 to the 0 power, you can use logarithmic differentiation to simplify that. Question?
So we couldn't just use y, we need to switch out y.
You need to, yeah, write y as x. So it's a true function of x.
So why did we bring down the original function?
Because that's what y is. And I don't want to have a function of x times y. I want a function of x times, I just want a function of x. I'm going to write everything in terms of x.
Okay, thank you.
So let's kind of use this technique to show y equals x to the r, where r is a real number. What is the derivative of x to the r? Yeah, right? So we should be able to do logarithmic differentiation and also show, using logarithmic differentiation, we get r x to the r minus 1. So if I take natural log of both sides, so I have ln of y equals ln of x to the r. Simplifying, I have ln of y equals r times ln of x. Taking the derivative of both sides with respect to x, 1 over y times dy dx, right, equals
R over X.
r over x. Very good. So now if I solve for dy dx, dy dx equals r over x times y. So that would be r times x to the r over x. What is x to the r over x? Like bases, if I have x to the a over x to the b, I write that as, yeah, x to the a minus b. So here I have r x to the r minus 1. And we're happy, right? It's the same thing we got before by using the power rule. So note, if I have x to the a over x to the b, I write that as x to the a minus b. And that gives me the same thing. Logarithmic differentiation is a technique. You can apply it in other instances. However, generally, you will know when you need to apply it. Or it will say, use logarithmic differentiation. On the final exam, it might say, differentiate this function. It might be more complicated than that, and so you want to use logarithmic differentiation on it. So you kind of get the feel for when it's beneficial and when it's not. Question? Oh, sorry.
So is it that will be told if we have to use the logarithmic differentiation?
If you have to use it, you'll be told. But sometimes you will need to use it, and I won't tell you to use it. We'll do an example where you can do multiple different ways on Wiley, and both logarithmic sometimes is easier. Later on, we'll learn the derivative of e to the x and how that comes, and you can do logarithmic differentiation there because ln of e will cancel, right? So if I want to find the derivative of e to the 6x, I can take ln of both sides and simplify it, or you can just know the form for e to a power. I've seen students do it in some really weird instances, and it comes out okay. And I've seen students apply it just fine. So you kind of get the feel for where you need to apply it. If I want you to use it, I will tell you to use it. But you might have a problem where you're not forced to use it, but you could. Or you don't have to use it, and it's not necessarily easier, but you can use it. Like something like this. This is not super hard, but it's a lot easier just to know what the form is. Okay, so let's look at, let's pull up some Wiley questions. Don't log me out. Let's see if it does. Okay. So, what is the derivative of ln of 2x?
1 over 2x.
Times the 2. 1 over 2x times 2. What is 1 over 2x times 2? 1 over x. Ln of 9x would be 1 over 9x times 9, so you get 1 over x. You guys see that? So, let's see if I can simplify this a little bit. So Wiley problems. So if I have y equals ln of 2x, y prime is 1 over 2x times 2, which is simply 1 over x, right? This next one I did in the previous class to show that there's two ways to approach this one. What is the derivative of ln of x over 5 plus x squared? Quantity, x over 5 plus x squared. So it's kind of...
Use a chain rule or you can break it out.
Yeah, exactly. You can use the chain rule and the quotient rule, or you can break it out. So you have, this is number 7. So this is like number 1. Let's look at number 7. There's two ways. Your answers are the exact same, but they might look different. One has a common denominator, one doesn't. So two ways to do this one. I could take y equals ln of... The first way, just doing the product and quotient rule. The chain rule and quotient rule. Sorry, the chain rule and quotient rule. So let's do the chain rule and quotient rule. So what is the derivative of ln of x over 5 plus x squared?
1 over all that.
Yeah, 1 over all that, right? times the derivative of the inside. What's the derivative of the inside? Derivative of the top, hold the bottom, minus derivative of the bottom, hold the top over the bottom squared. So the derivative of the top is 1. So 5 plus x squared minus 2x times x over 5 plus x squared. Right? So now I need to simplify some things. So I'm going to minimize this for a minute. So now I need to simplify some things. Simplifying this, I get 5 plus x squared over x, right? 1 over a fraction, a flip and multiply. So then I have times 5. I have x squared minus 2x squared. So it would be minus x squared. Five plus x squared, quantity squared. So this cancels with this term. And I'm left with 5 minus x squared over x times 5 plus x squared. So that's one answer. So this would be one way. Let's look at a second way. What's another way to write ln of a divided by b? Good. So I could write this as y equals ln of x minus ln of 5 plus x squared. So y prime is going to be 1 over x minus 1 over 5 plus x squared times 2x, right? Oops. So simplifying that, I get this. Do you guys see how these are the same? If I had a common denominator, they would be the same. Wiley will accept both answers on that. So that's kind of what I'm saying is there's more than one approach to these problems. Sometimes if you're creative in the beginning, it saves you a little bit of work and potential algebraic errors. So let's go back to Wiley, see what our next question is. So this example is telling you use logarithmic differentiation. Use logarithmic differentiation to do this problem. So let's look at this problem. This is like number 35. So I have y equals x, the sixth root of 1 plus x to the 7th. So this one's not horrible. It's possible we could go through, take the derivative of the first function, hold the second one plus the derivative of the second one, hold the first, the product rule. It's not too bad, but it says to use logarithmic differentiation. So logarithmic differentiation, I take natural log of both sides. Can you guys see that I can write this as ln of x plus 1/6 ln of 1 plus x to the 7th? Are you guys comfortable with seeing that at this point? So now, this is as simplified as I can get it. So I want to take the derivative with respect to x. What's the derivative of ln of y? Very good. 1 over y times dy dx. Derivative of ln of x, 1 over x, plus 1/6, 1 over 1 plus x to the 7th, times 7x to the 6th, right? So if I solve for dy dx, 1 over x plus 7x to the 6th over 6 times 1 plus x to the 7th. All that multiplied by y, right? And y is x times the 6th root of 1 plus x to the 7th. So that would be your answer there. If I multiply this in here, you can see that the derivative of the first function, hold the second one. When I multiply this in here, I just get the second one, right? The derivative of x is 1. So you can see it's going to be the same thing. It might not be in the exact same form, but you can simplify it to that form if you want to show that. Anyone have any questions on that? Some of you are like, just catch up writing.
On the last one,
Mm-hmm.
I don't understand where the 2x was.
Shouldn't the 2x be on the outside of the whole thing on the last one?
This one or this one?
That one.
Like, on the first one, we got rid of the 2x and the
Here?
x squared, yeah.
Yeah, because x squared minus 2x squared is minus x squared. Here, the derivative of ln of x is 1 over x. The derivative of this would be 1 over 5 plus x squared times the derivative of the inside, which is 2x. 2x is only multiplied by this expression.
Okay.
Make sense? Because I do it term by term. The derivative of this term, it's all by itself. Minus the derivative of this term, it's all by itself. The 2x is multiplied by this term, though. But not the whole expression.
We're not using the logarithm.
We're not using logarithmic differentiation here. No. We are using it here,
Because it's y equals.
a function of x, and I take logarithmic differentiation of both sides. However, I mean, in this example, I'll come back to that one, but I want to do here. Not that one. Here. This is not logarithmic differentiation
Because it has a log.
because it already has a log in it, right? You wouldn't want to do logarithmic differentiation here. It's going to complicate things. Here, this is not logarithmic differentiation. It's already in that form, right? So I don't want to take ln of ln. So I take dy dx, and then I take the derivative of this side, which I want to split this up. It would be ln of this plus 8 ln of this minus 2 ln of this minus 4 ln of this.
Okay.
The derivative of each one of these is relatively simple. And if we have time, hopefully we'll get to that one. But you only want to take logarithmic differentiation when you have a really complicated function that doesn't have ln already in it. Here, I mean, it's like logarithmic differentiation, except you don't have that extra 1 over y step. You don't want to take ln of both sides. It's already kind of in that form for you. Okay.
On this last one, real quick, when we did the 7x,
Yeah.
where'd you get that from?
Be-
I know you took the.
The derivative of the inside. What's the derivative of 1 plus x to the 7th?
Okay, so you took the outside.
The form for ln of a function is 1 over that function times the derivative of that function.
Okay.
So this is the function, 1 over the function times the derivative of the function.
Okay.
Okay, so let's look at a chain rule within a chain rule of ln. So let's look at number 19. So I have y equals 3 ln of x. So it's the derivative of the outside, evaluated the inside times the derivative of the inside. So y prime is going to be 3 over ln of x, right, times 1 over x. So that's 3x times ln of x. Do you guys see that?
Why is the first one still ln of x?
Because minimize this here. So I held a constant. This is ln of a function. The derivative of the ln of a function is 1 over that function, right? Times the derivative of that function. And the derivative of ln of x is 1 over x. Times the derivative of x, which is 1. You guys see how there's a chain rule there? So the derivative of the outside evaluated at the inside. So the derivative of ln is 1 over what's in the inside. Times the derivative of the inside, which is 1 over what's in its inside, which is 1 over x.
So the derivative of 3 ln is just 3.
The derivative of 3 ln of x is 3 over x. Okay, so if you guys bear with me, I think it will be beneficial to do the tangent line problem. Okay, if I can go a minute over. So this is the setup. Remember I said I cannot take natural log of a negative number? This is a negative number, so I can deal with it. So don't get too caught up on that. So let's look at, this is number 43. So if I have the function ln of negative x. What's the derivative of ln of negative x? One over x, right? 1 over negative x times negative 1. So the derivative here is 1 over x. So if I want a tangent line, I need a point and a slope, right? Nothing's new. We just have new functions to deal with. So what is my point going to be? Minus e squared is my x point. What is my y point? Huh? I plug this in, ln of negative e squared. What's ln of e squared? 2. Yeah, ln of e is, and then the 2 gets pulled down, right? So this would be my point. What is my slope? Right? That's just a number. 1 over minus e squared is a number. I leave it as that. So I have a point, I have a slope. I can find the equation of the tangent line. Y minus y1 equals my slope times the quantity x minus x1. And then I solve for y. So this is going to be one where you have to enter weird numbers like 1 over e squared or negative 1 over e squared. But that's fine. That's a value. That's a number.
Like for like the f prime.
Mm-hmm.
So what would that be? Like 1 over x?
That's the formula. So I plug in x to be minus e over 2. So I evaluate this at x equals minus e squared. So I have minus 1 over e squared as my slope. All right, I will see you guys tomorrow and expect an email from me later today figuring out